Hello everyone, we are Jbing. Today we are going to present about cardiac resynchronization therapy with defibrillator. This presentation is a part of EGBI 330 Biomedical Measurement and Instrumentation. These are our group members. This presentation covers 6 parts, including introduction, proposed product, overall function, circuit, program, and ISO. First, let's start with introduction.
So, what is CRT-D? CRT-D is a device that combines pacemaker and implantable defibrillator together. So the patient that using this device will have two main groups. Group number 1 is the patient who have bradycardia or heartbeat less than 60 BPM. Group number 2 is the patient who has tachycardia or heartbeat more than 100 BPM. Or they can be the other group that heartbeat not in the rhythm.
Cardiac resynchronization therapy implantation is a minor invasive surgery below the collarbone. The device connects to the heart muscle with 3 leads, which are right atrial, right ventricle, and left ventricle lead. The lead is inserted through the subclavian or cephalic vein and travels through the superior vena cava of the heart. The ventricle will be implanted first to reduce complication of navigation and the risk of atrial lead dislocation. The lead position of RA is at atrial appendage. RV is at the right ventricle apex or ventricle septum. LV lead will pass through the coronary sinus and position at the epicardial vein on the free wall of the left ventricle heart.
Next, we will present our proposed product. These are the features of our device. They have a high-resolution electrocardiography with active second-order and digital filters. They are automatic measurement, analysis, and interpretation device that also come with the sensors and algorithm for activity rate response pacing mode and MRI-compatible function. The amplitude of output voltage can be adjustable. Also a long lifetime built-in battery and a built-in memory SD card to store the detailed data for the analysis report. The built-in Bluetooth in the device provides the telemetry system for sending all the information to external device. And lastly, we also provide the user with clinical annotations. Next is the specification of the device. The device has 2 main parts, which are the housings and the leads. The leads consist of 3 leads, which are for the right atrium, right ventricle, and left ventricles. The resolution of the device is 12 bits and the sampling rate is 1024 Hz. Their input impedance is more than 1 GΩ and their bandwidth is between 0.5 to 300 Hz. The defibrillation shocking power is at 40 joules and the pacemaker pulse generator is at 0.1 to 15 volts. The built-in memory SD card has 32 GB capacity. Next is the material. The first one is housing. The housing comes in a small size with oval shape. The material for the housing is titanium. Titanium has a high resistance for corrosion, high strength and durability, which provides the device with long lifetime usage. The battery we use in the device is lithium manganese dioxide battery with voltage at 3 volts and the load current is 1.9 amperes per hour and the lifespan is around 6 years.
For lead, it has a role in transmitting electrical signal between heart and pulse generator. There are 3 main components of the lead. First, the lead conductor is the conducting part allowing the current to flow along the lead. The conductor will attach to the electrode. The material of the wire is MP35N, which is nickel cobalt based alloy. MP35N has excellent conductivity and corrosion resistance. It has ultra high strength, toughness, and MRI compatible properties. The lead can have more than 1 conductor wire. The lead conductor is shaped into a single coil of multi-filament structure. Second, the lead insulator plays a role in separating the lead conductors. Silicone made 4719 is used as an inner insulation, and polyurethane 55D used as an outer insulation. Both materials are biocompatible and help prevent both physical and electrical transmission. Silicone is well known to be excellent in flexibility, biostability, while polyurethane has advantage in high tensile strength, high abrasion resistance, and low friction in bud. The third component is electrode and defibrillation coil, which are an insulated part of the lead. It is direct contact with the cardiac tissue. The electrodes are used to send the cardiac signal and deliver electric impulse to the heart. The material for electrode and defibrillation coil are platinum iridium alloy. This material is conductive material with high biocompatibility and chemical stability. It also has a high resistance to high temperature, low corrosivity, and good durability and inertness. For the connector block at the header of the pulse generator is made from polyurethane, which has insulation property. The connector pin is made of P1 stainless steel due to its high corrosive resistance. The connector pin is a part of the lead, which will connect to the connector block. The lead design and connector pin of each chamber will be distinct because of the different functionality and safety. From this design, the cathode electrode which has negative charge will be located at the tip of the lead. The anode electrode is at the ring. RV lead will have one defibrillation coil for high voltage shock. LV lead will have quadripolar electrode to increase sensing and phasing ability, and also avoid phrenic nerve stimulation. For connector pins, according to the current standard, the RA connector pin is IS1, RV is DF4, and LV is IS4.
Next, we will present our overall function.
Our circuit has several systems. First one is sensing system. It receives input and clean unwanted signal. Second one is the MCU. It acts like a brain of a circuit. It contains the program and the coding. Third one is the telemetry, which sends data to physicians and doctors. And the last one is shocking circuit, which are pacemaker and defibrillator that shock the heart.
And this is our overall flowchart, which will be explained more in the next slide.
First, each electrode will receive intrinsic cardiac electric signals, then pass it through the lead. Wire to connectors, each connector will separate into two wires to plug in 3 instrumentation amplifiers, forming 3 leads. Moreover, there are several external sensors that are Hall effect sensor, detecting MRI, impedance measuring circuit, and an accelerometer sensor detecting patient's activities. Secondly, after getting the raw signals of 3 leads, instrumentation amplifiers receive those signals, then create lead 1, 2, and 3. Then, those signals will be filtered by an active second-order high-pass filter and an active second-order low-pass filter. After amplifying, the signal by 2 non-inverting amplifiers, with each gain equal to 10, 2 amplifiers will equal 100. Before entering the microcontroller unit, we will use a polarity correction circuit to prevent reverse voltage from entering the microcontroller unit because it cannot be easily replaced.
Pre-filter analog signal will enter the microcontroller via built-in analog to digital converter or ADC channel 1 to 3 respectively. Then the digital band stop will either cut off frequency at 50 or 60 Hz depending on the country preference. The signal will pass through the digital EMI filter algorithm. Then the program sensitivity will classify the cardiac activity in each chamber. Its signal from RA, RV, and LV lead can be denoted as a different part of cardiac waveform. After that, the clock in MCU will count the time interval of detected signal cycle. This time interval is calculated into BPM via QRS and RR interval. Classifying the patient condition of bradycardia and tachycardia depends on the rate of BPM, which will have different program treatment operations. The sensor input parameter will also help determine therapy instruction from the microcontroller. There are two modes of response therapy, which are pacemaker mode and defibrillation mode. These two circuits will work only one at a time. In the defibrillation circuit, it consists of a high voltage transformer, comparator, and H-bit circuit. The pacemaker circuit will go through voltage multiplier, comparator, and H-bit. Lastly, both circuits will generate the biphasic signal to stimulate the patient's heart to function properly. The ECG data and treatment data will be collected and sent to the external device via telemetry system.
About the circuit, these are the components that we include in the circuit. The first circuit is a sensing circuit. We will have three of this one to forming three channels of signal with a lead 1, 2, and 3. Noises will get filtered out by high pass filter and low pass filter. After that, the non-inverting amplifier will amplify the signal up, and before getting into the MCU, polarity correction circuit will play a role. Next, our pacemaker composed of comparator and H-bridge circuit, creating biphasic signal, and also our defibrillator has transformer, rectifier, and comparator and H-bridge circuit, also for forming a biphasic signal. Voltage regulator we use to adjust the voltage to keep it constant throughout the entire circuit. Microcontroller, we chose this model because it has high resolution ADC, it has Bluetooth, and also high flash memory. For power inverter, it's used to amplify the voltage. Memory stick we use to attach the additional memory or SD card to the MCU. Next one is impedance measuring. We use AFE4500. It measures the impedance and send the data to the MCU. Hall effect sensor is detect electromagnetic interference and send data to the MCU. Also, the accelerometer is used to detect patient activities to see that whether they exercising or not and send the data to MCU. And for the memory management, in one day, we will use 1.4 megabyte per channel. So in 1 month, it takes around 256 megabyte. With our 32 gigabyte SD card, it will sufficient for around 10 years, but checking up frequently is recommended.
We calculate the battery lifespan. If a patient has 2 shocks during 24 hours every day, the battery will be able to supply the operation for about 6 years. The following signals is the shocking power and amplitude signal of pacemaker and defibrillator that we simulate in the Proteus using a digital oscilloscope.
We will present a program flowchart to show the details of program operation. This is the overall of our program flowchart. The program will start by counting the time interval of the intracardiac events and then calculating the blood pressure measurement to distinguish between bradycardia and tachycardia criteria. The criteria for this is if the blood pressure measurements are less than 140, it will be bradycardia. If it is more than 140, it will be considered whether the patient is doing the exercise activity or has tachycardia. So we have the accelerometer and the minute ventilation that can be calculated from the impedance measuring parameter to use to consider this. If it can detect that the patient is doing activity, it will adjust the pacing rate for bradycardia mode. And if there is no sign of the activity, it will go to the tachycardia mode. Another function for safety of our device is MRI mode. The magnetic field from MRI can cause the oversensing and undersensing, which can be harmful to the patient. The MRI mode works by detecting the magnetic field using a Hall effect sensor that will send the digital output to the program. If the device can detect the presence of a magnetic field, it will turn into MRI mode, which can be programmed to be DOO, VOO, or AOO mode. These modes are the pacing mode that then neither sense or respond to any event and will be paced based on the timer that is programmed differently for each three modes. If they cannot detect the magnetic field, it will go to the bradycardia mode, which is pacing mode. The mode we present here is the DDD mode. The DDD mode is the mode that can pace and sense from both atrium and ventricle chambers and respond in either inhibit or trigger mode. The main method in this mode is it will start with the initial timer that is programmed by the device. For both ventricular and atrial pacing, if they cannot sense any intrinsic activity within the timer period, they will pace the heart. If there are any sense intrinsic activity within the timer period, it will consider if that sense event can be accepted or not, using different criteria for ventricular and atrial pacing as shown in the flowchart. Then, after pacing or accepting the sense event, the timer will be reset to the different parameters.
In defibrillation mode, the program needs to discriminate supraventricular tachycardia and atrial fibrillation from ventricular tachycardia or VT and ventricular fibrillation or VF. The program will use the BPM detection zone to classify whether the heart rate is low VT, fast VT, or VF. Once the device detects, it will count the duration of cycle length to certify that the patient has that condition. This is because the high voltage shock is very dangerous and only required when necessary. For slow VT, it may need only anti-tachycardia pacing or ATP to take action, while fast VT and VF will require ATP during capacitor charging before receiving high voltage shock. For telemetry system, external communication is supported by the device wired Bluetooth radio frequency. The device can send both diagnostic information and a real-time electrogram to the patient's smartphone and clinical monitor for physician to follow up. With remote monitoring of patients, it improves survival and identifies risk markers of mortality for the patient. So this is the list of ISO regulation for the CRT-D device. This is the end of our presentation. If you have questions, please feel free to leave comments and we will try to answer them. Thank you.